This is a video going over our first big integration technique of the semester. This is integration by parts. The main idea here is we're going to undo the product rule. You can think about how U substitution really undoes the chain rule. We're going to try and do a similar thing here where we directly undo the product rule of differentiation. So we'll talk about how that works. We'll derive the rule. We'll maybe do a couple of examples. We're going to have to talk a little bit about setup here. We have some choices to make as we're going through integration by parts, and so I'll try and help build some intuition for how that goes. And then we'll use integration by parts to do some more examples, get some antiderivatives for a couple of elementary functions that we're missing antiderivative rules for, and that'll be everything that we talk about in this video. Relatively example heavy, which maybe will be nice, maybe not, we'll see. All right, so here's integration by parts. The main idea, like I said, is to undo the product rule in a similar way that U substitution undoes the chain rule. The product rule says if you have a function that's a product of two differentiable functions u and v, then the way that we do things is we look at u times the derivative of v plus v times the derivative of u, commonly written as uv prime plus vu prime or some other combination of this. So we're basically taking one function, multiplying it by the derivative of the other, and adding it to the swapped term, that second function multiplied by the derivative of the first. So what we're going to do is we're going to integrate this product rule. So I've set up an integral on the derivative of uv, and that's going to equal the integral on this uv prime plus vu prime. Notice on the left, if we integrate the derivative of uv, we're going to get uv. We may end up with some other constant of integration. We're at least going to get the family of antiderivatives that look like uv plus some constant. Notice, though, since we have integrals over here, I'm just going to move the constant over to this side and wrap up the constant of integration at the very, very end. So you could think there's really like a plus c here. But again, we're just going to move it afterwards anyway, so it's really not that big of a deal. So then, on the right side, I'm just going to split this up across the sum. I know that if I'm trying to integrate a sum of two functions, I can look at the sum of the integrals. And then what we might notice is that we have v prime dx and u prime dx here. And those, by definition, are differentials. I'll show you that a little bit in a second, but depending on how you define differentials in Calc 1, that might just fall out right from there. If we use the differential notation for those derivatives, you can see that v prime is really dv over dx, and the dx's you can think of like canceling out. And similar, we've got u prime being du over dx, and the dx's can cancel. And so we're just left with u times dv and v times du here. So that's commonly how we write this. So here's integration by parts. Suppose that u and v are two differentiable functions. The family of antiderivatives for the function uv prime. Notice, not u and v. A function multiplied by a derivative of a different function is uv minus the integral of v u prime dx, but normally it's written this way. This is how you'll likely see integration by parts. The integral of u dv is equal to uv minus the integral of v du. For the definite integral, we just add limits of integration everywhere that you would expect to add them. We evaluate that uv from a to b, and then when we find our antiderivative of v with regard to u, we'll evaluate that from a to b. Notice one thing really quickly. We have two parts to our original function. One of them is a function, and one of them is a derivative. And we need the other two parts. So we're going to differentiate u and anti-differentiate v prime. Remember, we start with u and v prime. And so we have to differentiate one part and anti-differentiate the other to get this rule for integration by parts. So let's take a look at an example. We have to pick two pieces here, one of which we're going to differentiate, one of which we're going to anti-differentiate. I always lay my stuff out in the same way. This is pretty standard. I'll maybe use some other colors here, though. Oops, I want du here. And v. So we're going to pick u and dv from our integral. Notice I didn't write v prime, I used dv. That means we're going to need all of our differentials in this as well. And once we've picked those two, we can find our other two pieces. So Normally, when students start this, we don't really have any intuition on how to pick any of the pieces yet. Maybe you could stare at it for a little bit and figure out what might be good and what might not. But for now, let's just go left to right, and we'll say, all right, let's pick x to be u, and, oh boy, there we go. And that leaves e to the x dx as dv. Notice we have to include this differential in here. You'll see why that's important when we translate things, hopefully. Now we can find du. That's not hard. That's just dx. And v is going to be the antiderivative of e to the x, or one of them at least, and I'll pick e to the x. Now, remember our formula. We had this u dv integral being equal to uv minus the integral of v du, meaning we're going to look at we're going to look at these two things and these two things. We're not going to look at these two things, because what you'll notice is that when we go back to the product rule, here it is, we started with one of those things already, so we need the combination of the two functions, and we need the other combination of function and derivative. So that's where we're at right now. We've already done this dotted line one in our product rule. We need to find the other two. So u times v is going to be x e to the x minus our integral of v du. That's e to the x dx. That looks great because I know what that integral is. So I'll just leave this as x e to the x minus my integral of e to the x is just e to the x, and then I'll tack on this constant of integration. You could think, oh, that's the constant for this integral, but really it's the constant for the whole thing. All right, not too bad, right? You can rewrite this in a couple of different ways. You can factor out e to the x and write it as x minus 1. These are the two main ways that you'll see it. Just for fun, what I'd like to do is see what would happen if we switched our pick. So let's take a look at this integral again. X e to the x dx, and we're going to set up a u and a dv again, and once we find those, we'll find du and we'll find v, and I want to swap our picks. In our first way that we did it, we said u is equal to x. Now let's say u is equal to e to the x, and that means dv is x dx. All right, we can find the rest of these pieces then. Du is going to be the derivative of e to the x times dx. And v is going to be a nice antiderivative form. We'll have x squared over 2. Now we'll go ahead and put things into this formula. uv e to the x squared over 2 minus our integral of v du. And that's x squared e to the x over 2 dx. And what you'll notice is that even if we factor some stuff, pull out that coefficient, we end up with an x squared e to the x dx. And you'll notice what we changed was our exponent on x got bigger. Whereas if we look at the exponent on x here, you could think that's really like x to the 0 e to the x, right? Our exponent got smaller in this case because the derivative of x is x to the 0, but when we anti-differentiate, our exponent gets bigger. This is going to be something we'll try and keep in mind here. We have to balance and juggle between differentiating one piece and anti-differentiating the other. So when we pick what u is going to be and what dv is going to be, we want to think about this. When we differentiate this power function x to the 1, it goes away. That's great, because we want to include that part in our second integral. Oh, it looks like my differential up here got mixed up. There we go. We want to include that in that second integral. So if this x to the 0 is just a nice constant, then this second integral, v du, is going to be a little bit easier. Whereas in this case, our exponent got a little bit bigger. We got further away from only having one function type there. Not so great. So that's something to just start keeping in mind. Let's try this example. I will encourage you to just go ahead and set things up on your own, pause our video here, and see if you can figure out how this thing is going to go. Take a look at the last example, try and replicate what we've done a little bit, and you'll notice it's a little bit different because now we've got an x squared function and a sine of x function instead of just a singular linear x and an exponential e to the x. So now we've got this quadratic x squared and this trig function sine of x. But take a look, see what happens when you plug things into place here, pick out a u and a dv, and things should go pretty well. Pause the video, and in a minute we'll pick this up. All right, we're back. Let's do this. X squared sine of x dx. My guess is that that's how most people started because we said, oh, look, differentiating this power function is going to be a good move, right? Now, our antiderivative of sine x dx is going to be a nice negative cosine function. Of course, there'll be a constant of integration, but we'll just worry about that at the very end. We'll tack that in place. Notice that we have to be careful about the signs, positive and negative here. It's really easy since we're doing a mixture of differentiation and anti-differentiation to get those things backwards. All right, let's put things into place. uv, that's going to be these two right here. We've got a negative x squared cosine x minus the integral of v du. I'm going to pull the 2 and the negative sign out front. So this is really plus 2x cosine x dx. All right, notice we still have an ugly integral here, but it's a little bit kind of, quote, better in this case. Because we went from an x squared parabola down to a linear x, we're moving in the right direction, right? So maybe let's go ahead and do this again. For this integral, we'll pick u to be x and dv to be cosine x dx. Now we can find du, that's going to be dx, and v, that's going to be sine of x. So now we still have this negative x squared cosine x plus 2 times these things. uv, that's going to be x sine of x minus the integral of v du, that's sine of x, and then just this nice differential dx. We've got some distributive property to do. I'll do it first. You don't have to. You could figure out this integral first if you wanted and then multiply, but let's just write this out. Negative x squared cosine x plus 2x sine x minus 2 times our integral sine x dx. This integral is something we can do. Negative x squared cosine x plus 2x sine x. Our antiderivative of sine is negative cosine, and so this is plus 2 cosine x plus c. So we have 2 rounds of integration by parts here, and you could imagine what would happen if that exponent on x was a lot bigger. We'd have to do several rounds of integration by parts to keep lowering that exponent as we differentiate that power function. So that's something to just keep in mind, that we may, with that second integral that we are left with, that v du part, the part that's highlighted right now, if that ends up being another integration by parts problem, we may have to repeat this process. No big deal. We'll just try and keep track of all of our signs, all of our coefficients, because those are things that are really easy to lose track of as we're going. I've got one more example before we move on, and then we'll do some more examples a little bit later. Give this one a shot. Set up our u and our dv, and then we can find v and du and put everything together. Pause the video, and you'll notice there's kind of a trick here on how we have to set things up. All right, even if you haven't paused the video for my other examples, pause it for this one. Try it on your own. All right, hopefully you've noticed the weird thing. We probably are, at this point, lulled into this false sense of security of saying, let's pick u to be x squared. Everything's great. I know what the derivative of that is. That means that dv is the natural log of x dx, and we're stuck. We do not know the antiderivative of the natural log function right now. We'll find out in a minute. But it's certainly not 1 over x. That's what a lot of students will jump to if they turn their brain off for a second. But what's the relationship here? 1 over x is the derivative of the natural log. So this is a wrong setup. It would be nice to differentiate that power function because we like it when those exponents get smaller. But we're kind of forced into picking natural log of x as u because we only know the derivative of the natural log of x right now. We'll keep that in mind in a little bit. That means that dv has to be x squared dx, and oh no, we're going to have to anti-differentiate this. We're up to x cubed over 3. Ugh, increasing exponents. It doesn't feel good, right? All right, so now we'll do our uv. So we have x cubed natural log of x over 3 minus v du. I'm going to factor out the 1/3 coefficient, and I've got an x cubed over x dx. Well, wait a second. This is good news. Because the derivative of the natural log is 1 over x, we can just reduce that power function. So sure, we didn't get to decrease our exponent to try and turn a log into the only thing we'd be left with, but because the derivative of a log is a negative exponent on x, it's x to the negative 1, we end up just getting a power function. Now we can integrate this really easily. So we have our x cubed natural log of x over 3 minus 1/3 times x cubed over 3, right? We're just integrating this thing again. So what we really have is x cubed natural log of x over 3 minus x cubed over 9 plus c. You can do a whole bunch of factoring on this. You could factor out an x cubed over 9, and then you're left with 3 natural log of x minus 1 plus c, or you can just factor out an x cubed if you'd like, or you can leave it there. I don't really care, but that looks pretty good to me. So we know that picking power functions for u is sometimes nice, but this example shows pretty clearly that it's not always nice. So the question is then, how do we know what to pick for our parts? If it seems to change all the time, then what do we need to do? Now, there are a couple of strategies out there with some fancy acronyms where you can just say like, okay, just do this, then this, then this, then this. Here's your flow chart of things to check. And we'll talk about that, but I kind of think that it's a little misleading. What might be best is to just think, would I rather differentiate this part or anti-differentiate this part? And sometimes it comes down to which of these integration or differentiation formulas are going to be nice to implement. With that last example, we picked the log as u because we don't want to anti-differentiate it. We don't really know how to do that well. It's nice if we can just differentiate it, and so it happens really well there. So we have these classifications of functions. These are kind of the normal classifications that you'll see. Log functions, inverse trig functions, power functions, trig functions like sine and cosine, and exponential functions. And I've got them in this ordering because what I'm going to say is that derivatives are really nice over here, and antiderivatives are hard. I can differentiate the log function super easily. I don't know how to anti-differentiate it. Similarly, inverse tangent, I know how to differentiate that. The derivative of the inverse tangent of x function is 1 over 1 plus x squared. I do not know the antiderivative of the inverse tangent function right now. Power functions sit right in the middle because they're nice to differentiate. They're not hard to anti-differentiate, but we've noticed that it's not great when we anti-differentiate them because the exponents go up. Sine and cosine are kind of neutral, right? Because the derivatives and antiderivatives are all in the same form. They just bounce back and forth between positive and negative sine and cosine. And then the exponential function e to the x is even more boring because whether you differentiate it or anti-differentiate it, it doesn't really matter. So the stuff on the left end of this list is going to be more influential for what we pick than the stuff on the right. If you see an exponential function, it really doesn't matter if you pick that to be u or dv because all you're going to be doing is getting another exponential function out of it in either case. Similarly, for sines and cosines, it doesn't really matter that much. Once you kind of make your pick, you can stay consistent with it and things just fall into place. With these power functions, it's nice to pick them as u if you can, because we like to differentiate those things so the exponents get smaller. But if we see a log function or maybe an inverse trig function, those might give a lot of preference for u. So the idea here is that these two we prefer to differentiate. with a big exclamation point. This one, it's nice to differentiate, but don't sweat it. And with these two, doesn't really matter either way. Whether you differentiate it or anti-differentiate it, you're going to get really, really similar functions. So if you see logs and inverse trig functions, grab those up as your U selection so you can differentiate those things. If you don't see any of those, but there's some power functions, maybe it's nice to just grab the power function as U. If you see just sines and cosines and exponentials, those don't really matter too much. You can pick either one. Here's some more examples. This is a weird one. We said integration by parts is all about products of functions. I only see one function in this integral, and it's a log. So let's set this up. Let's go ahead and use the advice that we just found. Logs, I don't know how to anti-differentiate this, so if I pretend that this is a product of functions, I'm going to pick this as the U part. That way I know what the derivative is. That doesn't seem helpful because we just want the antiderivative. Notice, though, I picked this as U, and that means that just this differential by itself is dv, because I did not include a differential in that selection of U. Okay, now we're getting somewhere. What would I have to differentiate to just get dx? Well, x. Now we can use our integration by parts formula to multiply U and V, x natural log of x, minus the integral of v du. And look at that. That's just the integral of 1 dx. Now we've got x natural log x minus x plus c. So we can add this to our running list of functions that we know antiderivatives of. From here on out, we can say the antiderivative of the natural log function is x natural log of x minus x plus c. That's the family of antiderivatives. That's pretty good. Let's do the same thing here with this inverse trig function, this inverse sine. So we'll say u and dv. We need then to find out what du and v are going to be afterwards. I don't know what the antiderivative of sine inverse of x is, but I know the derivative of it. I know that the derivative is 1 over the square root of 1 minus x squared dx. And that means that we're left with a dx here, and thus an x. And now, when we do our integration by parts formula, u and v get multiplied together. That's x sine inverse x minus my integral of v du. That's x over the square root of 1 minus x squared dx. That's not an easy-looking integral, but notice we can just do a u sub. There's this nice composition here. I'll put a little -2, and I'll switch this. I'll multiply by -½ on the outside, so I'll make it a +½ because it was minus before already. So we're subtracting -½ times this integral. That means I've got x sine inverse x plus 1/2 times the integral of this part is my du, and then I've got 1 over the square root of u. I'll just call that u to the -½ I can anti-differentiate this by adding 1 to my exponent and dividing. So I'm going to get u to the 1/2 over 1/2. Division by 1/2 is really multiplication by 2. U to the 1/2 is really a square root. And then I've got my plus c. And now I can put this u back in place. I've got x sine inverse x plus the square root of 1 minus x squared plus c. That is the antiderivative family for the sine inverse x function. You can do the same thing with the cosine inverse function if you want, and it'll work out really, really similarly. These inverse trig functions are kind of nice to do in this case. Cool. All right, so now we're left with just some other weird situations that we might have. This is the last example that I'll show because this video would get really long if I tried to show everything that's cool here. So what you'll notice is that we've got exponentials and trig functions. And if you go back to that list here, we said that those kind of don't matter what you pick because one of them is going to just switch the trig functions back and forth. And the exponential, no matter what you do, it's just going to stay the exponential. I'm going to pick e to the 2x as my u, simply because when I do the chain rule to find du, that's a little easier to just whip through mentally than having to integrate here. I'm going to get a whole bunch of fractions if I have to integrate that part, but it's not a big deal. All right, so we need to find du and v. Du is going to be 2 e to the 2x, or e to the 2, I said that right, 2 e to the 2x. I thought I stumbled over my words there. My antiderivative of the sine function is going to be negative cosine of x. All right, so let's start putting this thing together. This integral is equal to uv, that's negative e to the 2x cosine x, minus the integral of v du. I'm going to say plus 2 times the integral of e to the 2x cosine x dx. So I factored out this negative and this 2 here, so it switches the sign. Notice that the integral that we have here is very similar to the one that we started with. So because it's so similar, let's use the same kind of setup. U is equal to e to the 2x, dv is equal to now cosine of x dx. That means that du is still going to be 2 e to the 2x dx. Oops. There we go. And that means that v, the antiderivative of the cosine function, is going to be sine of x. And again, we'll worry about all the constants of integration a little bit later. All right, I'll try and give myself a little bit of room here. I've got e to the negative 2x cosine x plus 2 times uv, so that's e to the 2x sine of x, minus my integral, I'm going to pull the 2 out front there, of e to the x sine x. Oops, I forgot my 2. E to the 2x, there we go, sine x dx. Let me write out what we've done so far. The original integral, because this is getting kind of messy, the original integral of e to the 2x times sine of x dx is equal to, there's supposed to be a, oops, I put the negative up in the exponent. There we go. Sorry, it's equal to negative e to the 2x cosine x plus 2 e to the 2x sine x minus, there's this 2 and this 2 here, so this is 4 times the integral of e to the 2x sine x dx. Now what I want you to notice is that this integral is exactly the same thing as the thing that we started with. So what some people will do is they'll just call it I. They'll say this integral I is equal to negative e to the 2x cosine x plus 2 e to the 2x sine x minus 4i. And now this is just a little equation that we want to solve for I. We can see pretty clearly that you can add 4i to both sides, and you're left with 5i equals negative e to the 2x cosine x plus 2e to the 2x sine x. There's a constant of integration on here. I'll tack that in a second. Now I can just divide by 5, and I've got that my integral, I, which is e to the 2x sine of x dx, is really equal to a fraction over 5 plus c. I'm dividing by 5, remember, and I'm going to write this as 2 e to the 2x sine of x minus e to the 2x cosine x. Now you can do a bunch of factoring if you'd like on this because there's this common factor of e to the 2x, but this is kind of a clever way of solving this integral. Because this trig function, sine of x, just bounces back and forth between cosine of x and sine of x with the signs, positive and negative, switching, we can just apply our integration by parts formula until we see our original integral pop up. That's the one we've got highlighted, right? And once we see that original integral popping up, we can look at this equation and just solve for that integral. So that's kind of a neat way of doing things. All right, we're at half an hour. That's a long enough video here on integration by parts. There are tons of pretty cool examples of applying integration by parts to different situations and things like that. And we certainly will see a couple more throughout this semester. But later on in your life, you'll see a decent amount of this. Integration by parts is one of the most widely applied integration techniques in practice that I've seen. It's used a ton in statistics and in some physics and engineering stuff. And so if you're going into any of those fields, you'll see it, and it shows up in a bunch of other places as well, because it makes sense. We're trying to integrate this combination of functions where they may not necessarily have this perfect interaction like U substitution needs. So integration by parts, super applicable, super useful. Hopefully we get a little bit comfortable with that. We'll see more of these kinds of examples as we go through the course.